So let's start this lecture on bias and variance decomposition and also ensemble methods, the first part of it, which is on bagging. So here, what we want to do is to have a closer look at what determines the error of some machine learning algorithm, or in general, some estimation procedure. And after that, so this is basically giving us some more intuition of when machine learning algorithm perform well, or why it may not perform very well, and what are the different contributing factors to it. So this is going to be a bit more, so there are a lot of derivations on the slides, more than any other lectures that we had so far. So I think you need to kind of read it carefully and go through the derivations. You don't need to memorize them, but you just need to know what are the main things that has happened. So based on that, we get to this other concept called bootstrap aggregation or bagging. And then also I talked about random forests as one of the kind of implications of having the insight that we learned in this lecture. So I guess the things that you need to learn is that what is bias and variance decomposition, the concepts behind bagging and random forests. So let's start with bias variance decomposition. So here the idea is that in what we've seen before, we talked about concept of overfitting or underfitting, which was basically saying that a model that was very complex could overfit to data, maybe capture the noise in the data essentially. And if the model is very simple, it would underfit the data and would not capture the detailed behavior of how the underlying pattern of the data essentially. We kind of want to quantify this a little bit more precisely, and that is done through the concept of bias and variance decomposition. So instead of starting from a kind of a complex machine learning algorithm, we start with something very simple, which is estimating the mean, the average of a random variable. So this is the simplest learning method or learning problem, that we want to estimate a mean of a random variable given some bunch of samples from it. And then later we generalize this, and here we talk about bias and variance decomposition for this, and you understand what each of those mean. And then after that, generalizing it to a more general machine learning algorithm, for example, regression method, would be much easier. Okay, so what is the setup? The setup is that we have a random variable y, which has a distribution p, but we don't know the distribution. This random variable, of course, has a mean. Suppose the mean is well defined, so the distribution has a finite first moment. But it is unknown, so we don't know the mean. And the mean is, I denote expectation of y by n. And it has some variance sigma square, which is a variance, of course, of y, which is the same as I just had it in the previous lecture. It would be the expectation of y minus m squared. Now we have a bunch of data points, y1 to yn, with independently samples yi, which all of them are coming from the same distribution. So they are independently sampled and they're identically distributed, so they're IID samples. Now the question is that how we can estimate m using these data sets. Okay, so how can we do it? What is your basic solution? Just make sure that you're tracking the...
Compute the average on the data set?
Okay, perfect. Is that the only way we can do it? I'm not talking about good estimators, but just any estimator.
A median mode, maybe?
Okay, we can compute mode, yeah, or median. Yes, that's good. So these are all basic solutions and make sense. So let's talk about, okay, so we have these data sets, some independently sampled. Now what we consider is that we consider an algorithm, so a box that essentially gets data. So data set goes inside, and the output of it would be some estimate h, which would be a function of this data set d. So we can think of different algorithms. It's kind of some program on a computer does some calculations. Computing the sample average would be one of them. So what are some of the examples? As you mentioned, sample average. We take the we sum for I equal to 1 to n of yi's, and then divide them by the number of samples. And the other one is, okay, I call it single sample estimator. The algorithm just look at, maybe just erase here. So the algorithm only looks at the first data point, y1, and ignores the rest. That's a meaningful, that's an estimator. It is not a good estimator, but it is not a bad, it's a meaningful estimator. So we can imagine that. Another estimator is that it only always return value of equal to 0. This is usually a bad estimator because, well, it basically doesn't look at the data. The output of it is independent of data. So in almost all cases, it is going to be a bad estimator. Can you think of a situation that this 0 estimator is actually a good estimator? And by situation, I mean some property of distribution.
When the distribution is normal with 0 mean.
Okay, so that's a good one. When the distribution has a 0 mean, that unknown m happens to be 0, then this is a perfect estimator. It doesn't need to be normal or uniform. The only thing that is required is that m is m, which was the average of expectation distribution of 0. If it happens by chance that we are dealing with such a distribution, this is a very good estimator because it gives the exact value. But for any other estimator, that's a bad estimator. So this is kind of like super estimator, but a simple form of it, but it's not in general, it's a bad estimator. Now the question that we want to answer is that how well each of these are performing. When we have intuition that sample average is a good one, single sample estimator is not too bad, but it's not a very good one. And this 0 estimator is actually a bad one. Maybe, okay, so actually this is a good thing to think about. Why do we say such a thing? Why do we think that sample average is better than single sample estimator? What's the difference?
Well, intuitively, sample one takes more events into account, like more samples into account.
That's right. So it incorporates more samples into account to give an estimate. But why? Okay, so if I want to push a little bit more, why would it be better? Like other than that, like what would be the reason? What's the difference of them? Maybe more mathematically. Okay, so there is an answer here. In case the variance is high, single sample could be far different than the actual mean. So variance, when variance is high, direct sample is high, would be far. There is another question. I guess you sent it direct message, but that says subset of samples is more representative of data set. So maybe, I mean, larger subset of samples is more representative of data set. I guess that we can say that. The single sample could be at an extreme end. Yes, I mean, by chance, it can be a bad sample. I guess it's kind of like the first answer. Less violent, more stable. Yes, I guess that's another intuition. Like the single sample average is less relying on one sample, so it can be violently changed because we are averaging n data points. Another one is that it's unbiased estimator. Right, but if you actually think about it, is that both single sample and sample average, both of them are unbiased estimator. So you provided good answers. Let's try to make it a bit more formal. And as you can guess, we are going to talk about the bias and variance of this estimate. Yes, you have a question.
Yeah, it wasn't a question. I was thinking that maybe you could make it a little more formal. It is still intuitive, but by saying that, say for a single sample, the probability of it being like away or far from the actual mean by a given like epsilon radius on either side, if it has a set probability t, and then we have the assumption that the data points are IID, then it is d to the power of number of data points. That would be the probability of all of the data points being outside that radius. So we somehow, like, we're reducing the chance of all the data points being far from like the mean by having a large number of them, so that we have some good samples.
Right, yeah, I guess that's a good answer too. So probability of being far from true M would be higher when there's only single sample estimate compared to when we have sample average. I mean, you need to prove that, right? You need to use some, either say, depends on the mathematical tool that you want to use. You can use asymptotically, you can use a central limit theorem, you can use Hofting inequality or Bernstein inequality. We don't talk about that. We talk about somehow simpler formalism, but that's another way to think about it. Okay, so let's just try to formalize this. So the question is that how we can assess the performance of a particular estimator h of t. Ideally, we want h of t to be exactly equal to m, that is the expectation, but this is too much to ask. We can't really hope that happen. With a finite number of data points, we can't really estimate the mean without any error. So there would be some kind of error. The hope is that the difference between h of t and m would be close to each other. So how can we talk about closeness of two values? That this is a real valued number, this is a real valued number. How do we talk about the closeness of them?
Usually the difference?
We can talk about difference of them, right? So we do almost like that. We talk about the difference, but actually difference squared. So we use a squared error between h of t and m, which we don't know. So the whole thing is squared. So that would be denoted by error of t. So this, we use it as a measure of quality of estimator h of t. This is the same squared error loss function that we had in the regression case. So I guess one thing that is important here is that this error, the way that I defined, is a function of data set D. So if we have different data sets, if we get different errors D. So what I think I denoted or I wrote here is that, okay, suppose we have a data set D, which is y1 to yn. So we get some error D, which might be small. But suppose we get another data set, which is kind of from the same distribution, but just different independent set of samples. The loss error of D prime might be large. So what we now want to do is talk about average error, average of this error D, when average is over all possible draws of that data set D. So is this clear that error D is a random variable? Okay, so I guess one nod that I get in video. Okay, so perfect. I have two samples that it is clear. So it's a random variable, so we want to focus on its average or expectation. So what we do here is that we compute the expectation of this error, and the expectation would be over the randomness coming from choosing that data set D, which has n data point itself in it. So it would be, I'll just expand the error again. So it would be error expectation of h of d minus m, the whole thing squared. And as I mentioned here, the data set D is random, and this expectation is with respect to its randomness. So sometimes I use subscript something, random variable below this expectation symbol in order to denote what is the random there. Usually it is not needed, but here just to emphasize it, I may add it.
Excuse me, do you mind saying why is it a random variable? Is it like a function of the h function?
Because it's a function of h of d, right? So this is a function of h of d, and d takes d as input, and d is
and on different h of d's, we will get different error rates.
Yes, exactly.
Okay, thanks.
Different d's gets to different h of d, and as a result, different error of d.
But different d's, they come from the same distribution, right?
Yes.
Okay.
The same distribution, and assuming they're independently sampled. So it's a bunch of n data point independently sampled from distribution P, and then another n data point distributed independently sampled from distribution P. Okay, so now what we want to do, we want to understand the behavior of this expectation of, so what's happening? This term, expectation of a randomness of data set of h of d minus m squared, or error function. So by just looking at it closely. So these are we do some mathematical manipulation. So the way we do it is that we decompose this term by adding and subtracting expectation of h of d inside the squared term, and then expanding it. So what I'm doing here is that, so this term would be equal to, okay, this term would be h of d, m would be m, and in between, I have minus expectation of h of d plus the same expectation. So this whole thing would be 0, so I'm just adding 0, but I divided 0 to minus of expectation and plus of that expectation. And what is this expectation? This is essentially saying that, okay, so h of d is an estimate of the mean. Now I'm taking, sorry, h of d is not expectation. H of d is an estimate of the mean, m, right? So h of d is output of our algorithm. I take expectation of it over different draws of data set D. So how it behaves when we have different samples from, we give different data sets D to our algorithm for estimating the mean M, and then take average over all of them, or take expectation essentially. So this is what's happening. So I just now expand on the second line, I expand this squared term to 3 parts. I think we get hd minus e of expectation of h of d, the whole thing squared. So this comes from the first 2 terms. And now we have from the second 2 terms, we have expectation of over d of this whole value squared, expectation of h of d minus m, and then we have inner product of this term 1 and this term 2. So this is inner product of these 2 terms. Okay, so we have twice of expectation over data randomness of D of H of D minus expectation of H of D times expectation of H of D minus M, the true M that we don't know. So this might look a bit complicated. There are a lot of symbols here, but this is, I guess, basic decomposition. I'm basically doing A minus B to the power of 2. I think it's S. Okay. So this is the form. Now let's simplify the right-hand side. And we need some kind of, we attend to each term separately. So as a kind of preparation, we notice that if we have a random variable x, just a general x, and f is a function, the quantity of f of x is a random value. So we give a random input to a function, the output of the function would be random. But its expectation is not a random value. So the whole point of expectation is that it averages out the randomness of whatever inside it. So expectation of f of x is not a random variable. So we can say that expectation takes the randomness away. So expectation of d of h of d is not random, even though h of d is random. So now we are focusing on this term. Let me use a different color. Let's see if I have it different. Okay, so I guess I modified the slide here to make it a bit easier, more colorful. So this is clear. So this expression that I have, maybe I just remember to edit it. Okay, so we want to talk about these three terms, each of these terms. The blue term here, we have expectation of h of d minus m, the whole thing is squared. Recall that m is not random, m is the unknown mean, so there's nothing random about this. H of d is random, but expectation of h of d is not random, so the squared value of it is again not random. And if we take expectation of it, it doesn't matter because expectation of something that is not random just is the same value as what is inside the expectation. So this becomes the difference between expectation of h of d minus m squared. Is this clear?
So the expectation of the
Sorry, I can't.
The expectation of something is itself?
Yes, if the same random variable, yeah.
Oh, yeah, okay.
Yeah. It is essentially, I mean, very simplified. So we have expectation.
I understand, yeah, thanks.
Okay, perfect. So that's the second term. Let's talk about this inner product term, the orange one. So let's consider that term. To reduce the clutter, I use m bar to denote the expectation of h of d. So the expected value of the estimator, which is may or may not be the same as m. So in general, it is not the same. So m bar is the expectation of random variable, so it is not random, as I said in the previous page. So what we have is that if we have expectation of m bar hd, m bar can come out and becomes outside the expectation because m bar doesn't have any randomness in it. So we get m bar of expectation of hd, which is again, so this is general thing. So let's just write this inner product term. So the inner product term, we have hd minus expectation of hd, which would become m, be denoted by m bar, times m bar again, minus m. So this term the green one that is not random. There's nothing as a function of data set here. So it comes out of the expectation. So we get m bar minus m times expectation of what is remained here. So again, m bar comes out of it. So we have expectation of HD, the first term, minus m bar. But HD, expectation of HD is exactly m bar. So this whole thing would become 0, the second term. So this term becomes 0. So it would be m bar minus m, which may not be 0, but we are multiplying by 0, so we get 0. So inner product term becomes 0. So we dealt with this term. We dealt with that term. I guess we need to deal, and now we just have the last term, and it appears in our result. So if we do all this simplification, making inner product equal to 0 or having it equal to 0, and doing the other simplifications that we had, arguing about the expectation of something that is not random, we get these two. We can write expectation of our estimator minus the true mean, which we don't know, squared, would have these two terms. The first term, which is called bias, and the second term is the variance. So the first term is expectation of HD minus m squared. So it basically says that in average, how far our expectation is, or sorry, the estimator is from the true m. If it's an unbiased estimator, then this bias term would be 0. But if it is biased term, this expectation of h of t may be different from m, and in that case, the bias would be a positive value. And the second term is the variance of our estimator. So you can see that this is second term we have is expectation of h of t minus expectation of h of t. So remember that, and the whole thing squared, and then we take expectation with respect to data set. This is variance. So just to kind of remind you, I think I wrote it actually twice today, but maybe it helps to have it handy. So expectation of some random variable, let's call it z, minus expectation of z, the whole thing squared, would be, that's definition of variance. And you see that here, z plays the role of, or HD plays the role of z, and this term plays the role of this expectation. So this can be also written as the variance of what? H of t. So the bias is the error of the expected estimator over different draws of data set compared to the mean m of the random variable m. Why? Variance is the variance of a single estimator, HD, whose randomness comes from again t. So one single estimator, how different it is from this another same estimator with different random draws of data set that determines the variance of this single estimator. So this is the bias and variance decomposition for a mean estimator. Soon I talk about how we can extend it for a more general estimators too. But let's talk about, let's compute the bias and variance of a few estimators that we had seen, like sample average or single sample estimator. So recall that we had m was expectation of y, sigma squared was the variance of it. So sample average was estimator that was computing, summing yi's and dividing by n. So the bias of it we can compute it. So the bias term would be expectation of h of d minus m. So to compute it, I just plug in the definition of h of d here. So h of d was this summation minus m squared. And then I reorder the summation and expectation. So it would be equal to 1 minus n summation over 1 to n of expectation of yi. But expectation of yi is the mean of that distribution, right? And so this would become, each of them become m. So we have n summation of terms m divided by n. So it would be m total. So we get m minus m squared, which would be 0. So sample average doesn't have any bias. But what about the variance? So we can do these calculations for variance again. So we just plug HD and expectation of it. So what we get is, again, 1 over n summation of yi minus expectation of that, the whole thing squared. And then we can do some manipulation. We put, so each of them, the expectation of each of them would be equal to m, its expectation. So I put x, and I can change the order of expectation and summation. So after some simple manipulation, I get that I have 1 over n summation over 1 to n of yi minus m squared. But just look at this. I mean, I know this is probably simple, but I just want to be. So this term is essentially this variance of random variable yi. But yi is for each of I equal to 1 to n. They are coming from the same distribution, so they have the same variance. So it would be n comes out of this expectation. Because of squared value, it would be 1 over n squared. We have summation over 1 over n of yi minus m squared, the expectation of it, which is equal to the variance. So we get 1 over n squared times n of these points of summations or components of summation and sigma squared. So it would be sigma squared divided by n. So that would be the variance of our estimator. So now we put the bias and variance together. So it basically says that if we have the expectation of HD minus m squared is equal to bias plus variance. Bias is 0, variance is sigma squared divided by n. Okay, so this is, what does it say? Considering the discussion we had earlier, like 20 minutes ago. What is the effect of n on the error of our estimator? Okay, yes, when n goes to infinity, h of d is accurate estimator. So, or as n becomes larger, the error between our estimates and the true m becomes smaller and smaller with a rate of 1 over n. The error depends on the variance of the random variable y. So you see that sigma squared appears in this error here, but it would be diminished with the rate of 1 over n. So as you can imagine, if we have only n equal to 1, the variance would be the error would be larger the way it's defined when compared to when n is larger. So single sample estimator, it would be exactly the same. It would be a special case of it. So I just skip it, just mention that bias and variance decomposition would be 0. It is unbiased, but variance is high, sigma squared. And for zero estimator, we can see that the variance is 0 because there is no variation in it, but the bias is m squared. So the whole bias and variance would be m squared. And this would be only small when m, the true m, which we don't know, is actually very small value. But if m is large, this zero estimator would be bad estimator. Okay, so just a summary, we have sample average. Okay, so these are the summary of the results. I think I mentioned all of this. So yeah, maybe I guess another question you can think of it is that the sample average has zero bias, but it has a non-zero variance. And the question is that when does it have a zero variance? Can you think of it?
When n is very large, when we have the whole data set?
Well, suppose n is finite. Right, so when variance of y is equal to 0. So when variance of y is equal to 0, the sample average doesn't have any variance, which basically means that our random variable y doesn't have any variations. It is essentially just a single point all the time. So the distribution p that we have, say for example, if we have, I guess, so if I write the density of p of y, so it basically means that the density is concentrated in one point instead of being like having a variance. So if there is no stochasticity in the samples, we don't need to have many data points. Only one data point is enough to know the truth. But that's a kind of just mostly an exception. Okay, one other thing that I want to mention is that we could also define error a little bit differently. So instead of having expectation of ht minus m squared, we can talk about ht minus y squared. So compare the error with a typical sample y, and then this would be the measure of expected squared error of ht compared to y instead of the mean. We can do the same decomposition or very similar decomposition. So I think I will skip that. But what we get at the end of the day is that bias-variance decomposition has 3 terms now. This is for different ht minus y squared. The bias and variance are the same, but we have another new term, which is the expectation of y minus m squared, which is called the Bayes error sometimes. So this term is essentially, what is it? This term is the variance of y. So this additional term is the variance of y. So this is coming from the randomness of the random variable y, and it cannot be avoided. We can't get rid of the, if we want to compare with y here, we cannot get rid of this minimum variance that we have because of randomness of y. And this minimum error is called Bayes error. And this is kind of like the randomness that is in the data set that cannot be avoided. And in the case of this mean estimator, it would be essentially the variance of that random variable. Okay, any questions so far? So let's, I guess there's a question, what is y here? And then I come back to the question before that. And just make sure I'm not, so y is the random variables that we have. So the setup is, recall, we have random. The setup is that we have yi's coming from distribution P, and the expectation of that y is called m. So that is y. So going back to your question, the other previous question, is the reason behind choosing the square difference between ht and m and define bias-variance based on that, the same reason as choosing the squared loss for linear. So what was the reason for that? Squared loss for the linear regression. Are you referring to maximum likelihood estimation and Gaussian distribution?
Yes. So I remember that we had this interpretation that if we have a noise that is coming from the Gaussian distribution, then maximum likelihood estimation would lead to that choice of loss function. So,
right.
Yeah.
Well, I mean, that was an interpretation, but that wasn't kind of necessary for defining it. And I talk about it a little bit later today, actually, and it makes more, I guess one reason I'm going to explain in a few slides. The other reason is that it is convenient for calculation. We could also define it as the absolute different value instead of squared, but that makes this decomposition not as nice. But there is another reason that we see in a few slides, that having that squared error as the measure of error is meaningful in some sense. In a very good sense.
Yeah. So I was basically wondering if there's any reason besides like mathematical convenience. So you're saying that it does have some meaning.
Yes, there is another reason that is not even related to maximum likelihood. Yes, I get to it. So one thing is that can you stay for longer? Or like how many people we have?
I can stay, yeah.
Okay, I try to, I can stay about half an hour. I have another meeting, but I try to push it as much as possible. I guess you have enough material for your homework, so I'm not worried about that. But let's try to see if we can wrap up at least this bias-variance decomposition part of it. So now we want to talk about general case instead of mean estimator. So we have a machine learning algorithm, like a regression estimator, whatever method, decision tree, KNN, like linear models or whatever, or regression or classifier. So can we have similar decomposition for them or not? So what I'm going to talk about is, the answer is that yes, we can have similar decomposition. I mean, the form of it would be a bit different. For regression that I'm going to focus, the form would be very similar. And this is usually in the terms of regression we talk about it. It gets a very similar form. But there are some differences. So, and one difference is that we are not trying to estimate a single real valued number, which was h of t belonging to some R, but we are trying to learn a function actually. So h of t is a function from input to an output, for example. Output is still for regression, is still real valued, but input is just belongs to some vector space. Now, one question is that, okay, so how can even we measure the error in this case? Like what point of X do we want to talk about? Like, are we talking about, so if we have an estimator, if you recall, I mean, we can write estimator at h of x and d, which is saying that it's a function of d, but define a function of x's. So which x should we choose here? So that's one question. The other thing that's important to talk about is what's the concept of best solution? In the case of mean estimator, it was kind of clear. We wanted to estimate mean as accurate as possible. So our ideal was m being expectation of y. So that was the reference point where the error was defined with respect to. What is the best solution here? And as you can see, I guess the question that you just asked, it turns out that we can get a best solution in regression, and that is related to squared error. Okay, so let's go through similar exercise, but we need a little bit of more notation. So suppose the training set is T consists of n pairs of xi and ti, and we assume that they are independently and identically distributed IID. I mentioned IID a few times, but here I guess the first time I'm not sure if it's the first time I'm highlighting it or I had it before, but it's good to know what IID means. So from a sample generating distribution P of samples, so basically means that Xi and Ti is one draw from distribution P of samples. One notation we require is that we can talk about distribution over X's, so marginal distribution, and also conditional distribution of target T, condition of X. So P of X is the marginalization of P of sample, which is a function of X and T over D of T. So we take integral over T. And the other one is the conditional distribution of T, condition of X, which is just, it's a probable joint distribution divided by P of X. X. So, I mean, this exact formula is, you know it from stats course. We are not going to use it, but I just wanted to define the notations, P of X and P of T, condition of X. So the other thing that we have is that, okay, so another distribution that we have is distribution over samples, over data sets. So P of data set is the distribution induced by training sets. So we have n samples. It would be distribution over n samples from that P sample. So a bit more concretely, the distribution of data sets, which is this term, which is x1 t1 to xn tn, is the product of probabilities of xi ti. And the reason we have product here is because we assume that samples are distributed independently. And because all of them are from the same distribution sample, not different distributions, because that we assume that all of them coming from the same distribution, so they're identical, hence IID. Okay, so let's get to kind of intuitions. Suppose we fix a query point X, and then we consider an experiment that we have a distribution, we sample from it, we don't know what that distribution is, we sample n data points from it, and then we run our algorithm, whatever algorithm it is, on that data set. And after we run that algorithm on the data set, we evaluate, we predict what is the target T for that query point X. So what does it mean? Visually, suppose here, this is what I'm showing here is the distribution, two distributions. So this is classification case. One distribution, red distribution, the other is the blue distributions, like one for class 0, the other for class 1. And we get samples, like we get 100 samples from each of them. So this is data sets, for example, D1. So you see that there's a bunch of data points, red and blue. I get another data set D2. From the same distribution, I get a different set of data points. Again, from the same distribution, but the specifics of those data points are different. And the same for others. So now what happens is that I run my algorithm, suppose it's k nearest neighborhood or decision tree or anything, using these inputs that are given here. So it does some processing, right? For KNN, there wasn't training phase, it was all test phase. So maybe I try to zoom a little bit. So now I have this query point, this orange point. And now if it is KNN, I look at maybe the K closest point.
Sorry, question. These axes aren't labeled. What are we, I'm having a hard time. What am I actually looking at? These red and blue plots, these are probability distributions of.
This top here, you mean?
Yeah.
Top. So these are distributions of two classes. Like the red one would be the distribution of, it would be contour of the distribution of class red. the blue one would be the contour of distribution for class blue.
But
So maybe one dimension, it would be easier to show because I can't. So so for the red one, suppose this is one dimensional input. If class is 1, the samples from class 1 comes from, say, this distribution, and samples from class blue comes from this distribution. So this is a class.
this is the probability for a given class.
Yes.
This is the probability distribution of the feature vector.
Exactly. Yes. So it would be P of t is equal to 0 conditional x, and for the other one for blue. So there would be an overlap between the features that we get between two classes. They are not completely separated, but they have maybe different shapes of distribution. Maybe give you an example.
So maybe you had like the x-axis is like, I don't know, like height or something, and like the red, I don't know, red is cat, blue is dog. If you ignore maybe those tails on the top side, dogs are probably going to be
yes, exactly.
bigger.
Yes, exactly. Like it would be something like that. So I guess an example that makes in one dimension makes sense is that temperature. Suppose you have a temperature recording for, say, winter from January to March versus March to end of May. I mean, there are May, or in that spring essentially would be a bit warmer, but there would be some days that is actually colder. So there would be overlapping the distributions. And now I give you one sample. The classification problem becomes that I give you one sample, classify whether it is of temperature, classify, I give a data set, and then for a new query point, I ask you whether if the temperature outside is 7 degrees, is it spring or winter?
Yeah. Okay.
So that's, this is just, and here what we have is two-dimensional case of it. Actually, we are going to talk about this type of modeling here a bit more, but I guess for this visualization, I kind of wanted to show how it may look like. So we have different samples. So, and here for this query point, green point, the cross point, I want to see what is the correct label. Is it blue or red? If it's k nearest neighborhood, I have to look at maybe the k nearest neighbor and decide what is the majority class, for example. Now I have another data set. Because of randomness of this sampling process, the neighbors are a bit different, right? When I look at it, my label for that green query point might be different, the output of my classifier. And the same for this third case. So here the point is that when you get different random samples of data set, your process, your algorithm, for even one single query point may give you different results. So there would be some kind of variance in it. So we want to talk about that variance. And there might be also some bias to it, which means that maybe this classifier has a tendency, has a bias towards always producing results in favor of one of the classes. So that would be the bias term. So we are going to talk about, we gradually formalize it more and more, but the focus would be on regression and not classification. Okay, so I guess this process, this kind of slides summarize what I described in the previous one. So I go through it quickly. So let us run our learning algorithm on each training set D, producing a regressor or classifier, HD. So HD, given fixed D, is a function from input to output or targets. So D is random. So H of D, which is a function of D, is also random. h of t is a function of t, and so the function h of t is a random function. So this is very similar to h of t that we had for mean estimator, that we get different output based on what data set we give. This is the same process, except that here, in the previous case, we had a random output, just a real valued number. Here, the random output is actually a random function. Now, fix a query point x, and we use h of t to predict the output at x. So y would be h of x and d. So y is a random variable too, because of randomness of t. So randomness comes from the choice of training sets. So if I want to write it kind of in a more compact way, this random h of t becomes a random function, and look at the value of that function at one single point x is random. So there's no randomness in x yet. I'm going to introduce it later. And I guess the result of previous samples for some algorithm, I think it is KNN, with some specific K, essentially would be these decision regions, like red region here and blue region here. And you see that the regions vary a little bit, different random points, different random draws of the training set. And now we want to see variation of it at h of x. We can do the same exercise for regression. Suppose there is a true underlying function that is like this, but we have a noisy samples from it. But the samples might be at different points, and they might be at they have a different amount of noise. So you see that these are samples here. In another case, we have samples there. And suppose we fit some function, some regression function to these data points using whatever method that you want to use. As a result, the results that what you get would be different fits that have randomness in it coming from the randomness of data set. So I'm repeating this many, many times just to make sure that you hear it enough so that by the end of today you remember it. Okay, so here this figure is essentially showing the possible random fits that we might have for some particular regression estimator. And you see that, say, for example, if I want to query this regression estimator at one particular point x, for example, at here, different estimators give me different values depending on the randomness of t. And we can even compute them. Maybe here what is shown is the histogram of the values that we get. So we see that there is a distribution that is concentrated around some mean, but there is some kind of variance around it. And what we want to talk about is first, where is this mean of this expectation? And second, mean of estimation, the expectation of these estimators at that point, and then also how much variations we have here. So that will be the variance part of it. Okay, so I guess this recap is just going what I said a few times. So I just want to mention that when x is fixed, this is very similar to the mean estimation problem for the regression case, for the regression estimator. So recall that in the previous case, like half an hour ago, I was talking about expectation of, we were talking about expectation of h of t and m, the difference between m squared. In mean estimator, ht was a scalar random variable, but we have h of t, which is a function. So it goes from x to t. So can we have a Bias-Variance Decomposition for h of t? So two questions, I already mentioned that, but to emphasize is that what should we do, what should we use instead of m? M was the expectation of random variable y, but here what is the equivalent of m? The second one is that how should we evaluate the performance when x is random? Let's see if I can. Yeah, I think we can go through this. So we have, first we try to answer the question of what would be the equivalent of a meaningful one. So suppose x is fixed, the best estimator in terms of squared error is the conditional expectation of the target value. Basically expectation of t targets for x. So this is for regression case. So target is belonging to R. So this, and I denote it by y star of x. So the best estimator, so what's the best estimator? The best estimator is the one that minimizes that squared error loss. So let's be a bit more concrete. So if we compute the expectation of y minus t, t has some randomness in it in general, condition on x, this expectation of y minus t squared condition on x, and search for a y that minimizes this squared error loss, which is defined at that point x. The minimizer would be this y star, which is the expectation of t, conditional expectation of t, condition on x. So what is conditional expectation? Conditional expectation of t, condition on x basically says that if I fix x, what is the average value of t, right? So that average value is the minimizer of squared error loss that we have. So that's the kind of interesting result that justifies why squared error loss is meaningful. Why? Because average value of t condition on x is a meaningful thing to have. So if we want to obtain that, we want to know what is, for a given x, what is the average value of t, we can do that by minimizing this squared error loss. So let's go through the proof. So we start by conditioning on a fixed x, and just expand it. So we have expectation of y minus t x. Here y is any value, t is random, so randomness comes from t. So we have y squared plus t squared minus 2yt. So y is not a function of x here, it's just an arbitrary y. So it comes out of expectation. And then we just divide this expectation, decompose it to two parts. One would be minus 2y, expectation of t condition x. Again, you see that y here came out of expectation because y here is just a value that is not random. So there's no randomness as a function of x here. And then we have randomness, we have t squared condition of x. And then what we can do is that we can relate t squared, expectation of t squared to variance of t. So remember that for random variable, maybe z, what is it? We can write it like this. So random variance of z is the expectation of z squared, the second moment, minus expectation of z, the mean, squared. So here, basically, from this point to these 2 points, I just used what I have there. Okay, so now what I have is that I defined expectation of t condition on x to be y star. That's the definition here, up there. So I just replaced that expectation with y star. So what I get is that y squared minus 2y y star of x plus y star x, the whole thing squared. This comes from this one, plus variance of t condition of x. So I can simplify this, and it is good to convince yourself that this is actually true, that it would become y minus y star of x squared plus variance of t conditional x. So the first term is non-negative, and it can be minimized when y is set to be equal to y star of x. So when I started here, I didn't say what is y, it was just arbitrary number. But here, in order to minimize this, so if I want to minimize y here, it's equivalent of minimizing this term. And you see that the second term, the variance one, does not depend on y, so it doesn't change the minimizer. But the first term is function of y, and the minimum of it would be when y is equal to y star of x. Right, so I guess that's what I have here. The second term does not depend on y. It is correspond to inherent unpredictability or noise of this t, of the targets, and this is a game called Bayes error. So this is not reducible, you can get rid of it. But the first point, the first term, y minus y star, if you happen to choose y to be equal to y to conditional expectation of t, that would be the minimum of it. So yes, and that's again like a justification of squared error, because if you want to find a conditional expectation of target conditional input, which is a meaningful thing to have, then using squared error loss, the minimum of it would be that solution. So that's the justification. If you care about something else, if you care about finding the median of that random variable instead of expectation of it, or some other statistics of t, then you need to use different loss functions in general. Okay, I think that would be, I won't be able to finish these parts, but almost done. But I think you have enough material for your first, second homework, the first question of the second homework. And the second question is about regression. So you already know it. We talk about, we have homework for classification later for the next homework. Okay, so any quick question?